And all right, so let's go. We're going to talk about elliptic curve cryptography. So let me come to my worksheet and get rid of the chat. And this is my lesson from last class. All right, so with RSA and the other techniques that we actually went through in detail. So RSA, is a public key method that can be used for digital signatures or encryption and decryption. So this is based on integer factorization. So there's no sort of like general group theoretic generalization of the integer factorization problem. But we also talked about some things that were based on the discrete logarithm problem, like El-Gamal. So both the El-Gamal cipher and the El-Gamal signature scheme are both based on the discrete log problem. And the discrete log problem, it's supposed to be a C, can be expressed in any group. So in ZP star, the way it worked for El-Gamal is you have some generator of ZP star, and you have some secret D, which is just some integer, and then the public key is beta, which is alpha to the D mod P, and the discrete logarithm says that given beta, P, and alpha, it's impossible to discover D. So you can't feasibly know D. Okay. All right. But just because of the particular nature of this structure, ZP star, it was necessary that P be, on at least 1,000 bits long. So this is somewhere in the range of 1024 bits, depending on how much security you want, and it could be all the way to, like 16,000 bits. And the same thing for RSA. So these have sort of similar, but with RSA it would be the size of the modulus n or something, or the constituent primes p and q have to be at least thousands of bits long. So the good thing about elliptic curve cryptography, the reason it's so interesting, is that you don't have to have these huge bit lengths. So to have 256-bit security with elliptic curve techniques, you only need 512-bit keys. So it's a factor of 2. So with the elliptic curve public key signatures and encryption decryption schemes, the number to get security level S, you need a key of size 2s. So that's much better than in this other setting that use ZP star here. So now instead of 1024-bit keys, we just need 256-bit keys. Okay, so one thing I meant to add, but I forgot to sneak it in, is that the discrete logarithm problem does translate to other group theory contexts, because all you're doing here is multiplying alpha times itself a bunch of times in some group. So this is just alpha times alpha times alpha times alpha, D times. So I can do that in ZP star, but I can also do that in any algebraic structure that just supports multiplication. And so things that do that are called groups. We've given the group axiom several times, so I'm just going to assume people know what a group is. So you can talk about the general discrete log problem. So the general DLP is you pick some generator of a cyclic group, G, but now it's just some group. And but alpha is still a generator, G is still a cyclic group, and you pick some secret D. So D is still some integer, so it's a secret integer. And you produce beta, which is alpha to the D. now I'm not going to say mod p anymore, but it could be that G is equal to, ZP star, because it's just a generalization of what came before. So that's possible, but it could be some other group, such as an elliptic curve group. So beta is again the public key, and so the public parameters are alpha and beta and G. So everybody gets to know those things, but given the public parameters, it's impossible to discover or it's practically impossible to discover the private parameters, which is the secret integer D. So with any group, you can do some version of all the things that employ the discrete logarithm problem, like El-Gamal. We didn't talk about it, but another like an improvement of El-Gamal's signature scheme is called digital signature algorithm, DSA, and that is also based on the discrete logarithm problem, and Diffie-Hellman key exchange is also based on the discrete logarithm problem. So all of these things you can do over any group, and it may be more or less secure depending on which group you choose. So obviously you can do it over ZP star. You can also, sometimes people do it over like GF 2 to the K or something like that. But there are security issues with this, I think. Just to give an example of a choice of a group where this is completely insecure, so if G is equal to Zn, so there's no star there, then solving the discrete logarithm problem is trivial. So for some groups it's easy, for some groups it's hard. For the elliptic curve groups, as far as anybody knows, it's hard. All right, okay. So elliptic curves have to do with curves. So maybe we should just look at a couple of plane curves here. So this is just going to be like some algebra 2 stuff. So just look at a circle. So a circle is an example of a curve. So you have the xy plane, and then you have the set of points that make the equation true. Oh, I accidentally just moved the toolbar for Zoom, which is not what I meant to do. How do I move it back? There it is. I didn't know I could move that thing. Okay. So now I'm going to draw a circle. There's something here that's like, yeah, there. That button lets you draw awesome. No, quite didn't get it. No, I can't draw a good enough circle that it even recognizes that I'm trying to draw a circle. There it goes. So you can make a circle, and what's the relationship between this equation and these points? So those are just the things that satisfy this. So in the simplest case, R is just 1, and you have the unit circle. And then everybody probably knows a whole lot of points on the circle from trigonometry. So this is like, what is, this is like square root of 3 over 2, comma 1/2 is 1 point on the circle, root 2 over 2, comma root 2 over 2. And then, the obvious ones like 1, 0 and 0, 1, and then a whole bunch of, other versions of this and other quadrants, and the circle has all kinds of symmetry properties. So what is it that makes one of these points be on the circle? Those points are on the circle because they're all solutions to this equation. So you can think of the solutions of this equation being a set, and in this case we can draw a picture. There's lots of other equations that we could draw. And the book points out, so it's we're talking about elliptical curves, but actually we don't use ellipses at all directly. What actually are elliptic curves have some kind of deep relationship with ellipses, which we're not going to talk about at all. But if A and B are positive here, then you can exaggerate the circle in one dimension or another, and so then you get something that's more like an ellipse, so that's a curve that's an ellipse, but elliptical curves, surprisingly are not curves that describe ellipses. It's something else. So a curve is just a set of points that satisfy an equation. All right. So now let's talk about an elliptic curve. So an elliptic curve to elliptic curve over. Now here you could put some group, but I'm just reading the book to you. The book has like an extremely abbreviated version of elliptic curves. I could give you books that have better presentations of elliptic curves than ours. Our book does a really good job with AES. That's like its real strength. But some other things are not so great. So an elliptic curve over ZP for P not 2 or 3, I guess, is the set of all pairs x, y, in ZP squared, which fulfill, I'd rather say satisfy, so which satisfy the equation y squared equals, or is congruent to x cubed plus ax plus b mod p. And these a's, so these a and b is a choice of parameter there, but they can't just be anything. So it has to be the case that minus 16 times 4a cubed plus 27b squared is not congruent to 0. So this is something called the discriminant of the curve, discriminant. And we'll say some more things about the discriminant. Obviously, this negative 16 is irrelevant to whether or not it's congruent to 0 mod p, because you could just divide that out. But it's part of the discriminant, and the sign of the discriminant gives some information about the curve. So I leave it in there. All right, and so if this condition that the discriminant is not 0 means that the curve is non-singular, and that just kind of means normal. Okay, so let's look at some examples. These are supposed to be curves over ZP, but all of this theory is motivated by the way these things look in the real numbers. So you can also plot this equation over the real numbers. So let's do that for a couple of choices of A and B. I'll come over to, too many windows are open here. Oh, right there. Okay. All right. So here I'm just using Sage to plot an elliptic curve. So here I moved y over to one side of the equation, but that's basically the equation from the notes. And here we're using a equals -2 and b equals +2. And you get a curve that looks like this. Kind of looks like an old keyhole or something. And you have to check the condition about degeneracy, or sorry, whether it's singular or non-singular. And this is a non-singular curve because this equation is false. So just for fun, I picked b equals 3, and then I pick a so as to just force the thing to be singular. So you can see, what are we trying to avoid here? Oh, sorry, this is jumping around a little bit. So this is an example of a curve that is singular. So what happens, I'm sorry that it just seems to be almost randomly moving around in the worksheet. I think what's happening is that it's executing the worksheet, and that's the pictures that are being created is pushing things around. Anyway, so here's an example of an elliptic curve over the real numbers that is singular. And geometrically, what singular means is that the thing it has a non-differentiable point. So right here, it crosses itself, so it's non-differentiable there. Another thing that can happen is that it has a cusp. So just a non-differentiable, like sharp point. That can happen when A and B are both 0. Oh man, this thing is really annoying me. So I'll that's what happens if you plot an elliptic curve over the real numbers. You get this nice geometric picture. But in the notes, you probably noted that it was actually being defined over ZP star. So man, if it keeps jumping around like this, I'm going to lose my mind. Is there something I can do to help this? Maybe I'm going to switch to full screen and get rid of that. So hopefully that will improve things. Man, I almost feel like somebody is purposefully effing with me. There, it just jumped completely by itself. Anyway, is somebody messing with me? Okay. Is it gonna stay like, bastard! I took a screenshot. I'm just gonna look at the screenshot. So let's go to pictures, and now let me share the picture because I have to do that. So here's the picture from the notebook that keeps jumping around. So this is you don't get a nice geometric picture when you work in the setting of a discrete group. It just looks kind of like a somewhat random set of points. It's not completely random. You can see that it has some symmetry properties, and some of the symmetry properties are sort of the same as with the real version. So in the real version, the thing is symmetric about the x-axis. And the reason that that's true is because the definition of the curve is y squared equals x cubed plus ax plus b. So that gives you two solutions. Y equals plus or minus the square root of x cubed plus ax plus b. And so that's why you get a point on the curve up here and then a corresponding point on the curve down there. So something similar happens in the discrete context. The discrete context, square roots are a little bit more weird. So in ZP star, there are some elements that that have no square root. So it turns out exactly half the points have square roots and half don't in ZP star. And if you do have a square root, then you have two square roots, and even in ZP star. And so it's kind of easy to see why that's true. So I think I'll just illustrate it. So suppose that x squared is congruent to q mod p. Then it's also going to be true that x times p minus 1 squared is also going to be equal to q, because p minus 1 is just like minus 1. So this is also going to be true, mod p. So this is kind of like you almost get the plus and minus thing that you did in the real numbers. So these do come in pairs, but it doesn't make like a nice curve that you can just take in with the visual part of your brain. All right, so let me clear here. So sometimes these curves look like this. Sometimes they're even more boring. They just look like that, just depending on your choice of A and B. In fact, there's we should probably just look at the Wikipedia page where it gives you kind of a gallery of them. Another thing that can happen is something like this. So let me just go through here and talk about the difference between these. Okay. So here's the x-axis. So x-axis is the line y equals 0. And if you look at one of these curves, if you put 0 in for y, then you get 0 is equal to x cubed plus ax plus b. So this is a cubic equation. You guys might know, or you should know from 105 or whatever, that if you have a complex root, then you have a pair of complex roots. So the number of real solutions here is either 1, in which case there's a pair of complex roots, or it could be that there are 3 solutions. And that's what makes the difference between these two possible pictures here. So this is what it looks like if this has exactly 1 real solution. This is what it looks like if the thing has 3 real solutions, and neither 0 or 2 are possible. Because if it had 2 real roots, then it has at most 3 roots overall. So it can't have just 1 complex root, because complex roots have to come in pairs. And it can't have 0 real roots because it's an odd degree polynomial, and all odd degree polynomials start on one side of the x-axis and then finish on the other side. So it's also impossible for it to have 0. So anyway, those are sort of the 2 main possibilities. And I'm going to come back to, sorry, you know, this, look, I've gotten myself into a mess here. This annotation thing really does not work well. Clear all drawings, close this, and let's come back to this. This is still jumping around. Yeah, it's really making me insane. So I just want to show you, let's just go to Wikipedia, and we'll look at elliptic curve. Wikipedia. And it has kind of a gallery of them to show you the different possibilities. So this is just what we were describing. Here's A equals 0 and B equals 0. Notice that there's a cusp here. That's an example of a singular curve. And it could be kind of like this, or have, you know, it could have a little head, or it could have a detached head, etc. So those are the possible appearances of the thing, at least over the real numbers. All right. So it turns out that when you have a non-singular elliptic curve, you can describe a kind of group on the curve, which is what's going to be for us an elliptic curve group. So now we'll think of the elliptic curve as just being the points on some elliptic curve. So the reason I write EC there is because I want to be thinking of the collection of all points that actually satisfy the curve. So let me draw a picture of one. So something like this. And so let's say that we consider 2 points P and Q that are in this set. So let's say that P is a point on the curve, and Q is another point that's on the curve. Okay. So what we're going to do is this set is going to become a group. And what is a group? A group is a set with an operation. And we're going to just denote the operation here by plus, because that's traditional. So how do you, given P and Q in here, what we need to do is, well, the first thing a group needs to be is closed. So if P and Q is equal to R under this operation, which we're about to define, it has to be true that R is also on the elliptic curve, right? So here's what you do. You make a line that connects P and Q. Sorry, that's not going to be a good choice. I have to go like right there. Is that right? Sorry, I'm trying not to exactly hit the x-axis. That's going to be annoying. I think I'm going to move Q here just to make things work a little bit better. Let's put Q over there. Turn off the ruler. So here's Q. All right, and now let's do the same thing. So you make a line through P and Q. Ah, man, it's harder than it sounds, isn't it? And then it intersects the curve in some third point. So with only some weird exceptions, that always happens. So if you make one of the qualities that these elliptic curves have is if you have 2 points on the curve in sort of random position, and you make a line through them, that line intersects the curve a third time in exactly one place. We'll talk about a couple of exceptions to that in a second, but that's generally what happens. So this gives you another point on the curve, and you reflect it across the y-axis, and then that is R. So this is basically where the elliptic curve operation comes from. So let me talk about a couple other things that happen here. So let me redraw the curve. So that's, that was most of it, but then let's talk about some sort of unusual or pathological things that can happen. So what happens if you have this P here, and instead of P times Q, you want to do P times P equals 2P. This, by the way, is just sort of, 2 is an integer, and an integer is not a member of the elliptic curve group because the elliptic curve group contains only, points. So the things in the elliptic curve group are the form x1, y1, and things like 2 are not in the set. So when you say 2 times p, you just have to be aware that that's just a compressed notation for what should really be p plus p. But anyway, how do you compute p plus p? You just make the tangent line. So p plus p is the tangent. You use the tangent line, then that intersects the curve at some point, and then you reflect across the x-axis, and this would be 2p equals p plus p. All right, okay. So let's keep going. So what else can happen? What if you have 2 points that are sort of, well, okay. So just talking in group theoretic terms here, right? Everything has to have an inverse. So for every p, there has to be some minus p. And just by general group theory, it has to be the case that p minus p is equal to 0. So I put 0 in quotes here because 0 is not a point on the curve. So we have to define some point on the curve that's going to act like 0. And so what kind of properties does that special point have to have? It has to be true that p plus 0 is equal to p, and also 0 plus p is equal to 0 because it's a commutative group. Well, that's always true for the identity, even in non-commutative groups. So instead of working just in the real numbers here, so this would be the real plane R2. All of this happens in so-called projective space. So what that means is that you understand there to be kind of there's a point at infinity which is on the curve, and we call that O. And if that doesn't make intuitive sense, it never will. You don't understand it. You just get used to it. So there's a point at infinity, and so that's sort of at the end of the curve on this side if you go infinitely far, and it's also at the end of the curve on this side if you go infinitely far. And what we're going to say is if you draw, here's p. So the meaning of minus p is the reflection of p across the x-axis. So for every point on the curve, there is an inverse, and it's just its reflection across the x-axis. So now, what is the sum of these things? So you make a straight line through here, and it's supposed to intersect the curve exactly one more time, and it does, except that it intersects the curve at this point at infinity that we've just added to the set. So now we reflect across the x-axis, but down here is sort of the same as up there. It's like Pac-Man. You go out one side and you come back on the other because it's projective space. And so this is also 0 down here. And so what we've just shown here is that now we can take off the quotes, but we have to give this thing like a little cowlick. So the identity element of this group is the point on the curve at infinity, which we call 0 with a cowlick. And so now we can try to determine if this is true. Is it true that p plus the identity element is equal to p? Let's see. So let's say p is here, and let's put O up here, and now I make a line connecting those, and I hit the curve at a third point, but then I reflect across the x-axis to get back up there, and it's true. P plus the identity element is equal to p. All right, okay. Now let me say one more thing about doubling. So doubling is gonna be important for the cryptographic applications of the curve. let's just look at, here's some P. So the way elliptic curve cryptography basically works, so this is the picture in real projective space, not the picture in ZP star. So in ZP star, there's no picture you can draw, but it's still basically the same thing that happens, just without the picture, just purely with the equations. So you start with some P, and now you draw a tangent line, and you reflect down. So that gives you 2P. And now you can double this again. Now let's do a repeated doubling. So this will come up here, and then you reflect down here. So now what you've got is 4P. And now you can do this again. Zoop. And now this hits the curve here, and you reflect down here, and this is 8P. So what's happening is I repeatedly double here is this curve is just kind of bouncing around at random. And if you select the parameters for an elliptic curve correctly, remember the parameters are this A and this B. You can do this, you can select these parameters in such a way that this is actually a cyclic group with a generator, like maybe P generates the entire group. What does that mean? That means that every element of the group is, if you just pick some random thing here, let's say Q, so Q is equal to N times P for some integer N. And just remember that this is just compressed notation for P plus P plus P plus P plus P N times. So you can, what happens here, this is not exactly the same as repeated doubling, because once you get to 8P, maybe you just want to add P instead of doubling, but you can do that. You get to 8P, then you can make this line, and then, oh, sorry, it has to go all the way down here and touch the curve there, and then reflect up. And then you have 8P plus P becomes 9P. So you can do N times P. In fact, the algorithm for doing this is a lot like the square and multiply algorithm, because N is going to be some god-awful huge number, like not quite as big as in RSA, but it still might be a number that's on the order of like 2 to the 256 or something. So it's going to be so big that you can't actually do this number of additions. But just like in modular exponentiation, you can do that in only 256 steps by the square and multiply algorithm. It's going to be exactly the same, except instead of square and multiply, it's double and add, because it's addition instead of multiplication. So we might go through that in more detail later, but it's just like exactly the same as before. You just have some number of bits here, so you have a binary representation of N, and that's multiplied times P. And then by repeatedly doubling what you have so far, you can add a 0 there, and make a place. And then you can add a 1 or a 0 into this newly created place by either multiplying in another P or not, or sorry, adding in another P or not. So you just repeatedly double to add slots, and then you add in a P if you want to change the recently generated slot to a 1 where N is expressed in binary. Okay. All right. So I know you're probably sick of me drawing these pictures, but I'm going to draw another one. So here we have this. All right, and we're still drawing pictures in real projective space. So let's say I have P here and Q here. And I'm just following the book here. Let's actually write down some coordinates. So this is x1, y1. In projective space, you don't actually, represent coordinates this way. There's also like an extra coordinate that basically says whether the point is at infinity or not, but let's just ignore that. So that's Q, and Q is going to be x2, y2. So let's say that you're just going to do some geometry, and you were going to compute, so here is the intersection point again, and then this is going to be reflected up to be this, and this is R, and R is equal to P plus Q using the elliptic curve group operation. So what is R actually? So how would you do it? So first you need to figure out the slope of this line connecting Q and P, and the slope is just y2 minus y1 divided by x2 minus x1. Okay, and now what would you do? Now you can use point slope form to define that line. Trust me, I'm not going to go far with this. I just want to kind of get us started here. So if we use point slope form to actually express this line, then what we would get is, y minus y1 is equal to s times x minus x1. Okay, so that's the equation for the line. And then if we wanted to find the intersection of that line and the elliptic curve, we would solve for y here. So y is equal to y1 plus s times x minus x1. And then the elliptic curve is given by the equation y squared equals x cubed plus ax plus b. And now if we wanted to find the intersection of the elliptic curve and the line, then we take this y and substitute it into this other one, and then we get s times x plus x1 plus y1 squared is equal to x cubed plus ax plus b, et cetera, et cetera, et cetera. And then we would find the solution xy, and then that would be this guy, and then you would just make the y coordinate negative and it would go up there. Okay, so there's a whole lot of algebra there that we're not going to do, but let me just tell you what it is. So if r is equal to some third point on the curve, y3, x3, y3, then the rule for generating r is, so first you compute s, and so I wrote s just as if it were the slope. It is, but you have to consider that you might be doubling instead of adding p and q. You might be just doing p plus p. So it's actually case-wise defined. This is y2 minus y1 divided by x2 minus x1 if p is not equal to q. But if p is equal to q, then you have the tangent line. So the slope of the tangent line turns out to be 3 times x1 squared plus a divided by 2y. This is if p is equal to q. Okay. So now once you have s, you can compute x3. x3 is equal to s squared minus x1 minus x2, and y3 is equal to s times x1 minus x3. Notice that x3 is a part of y3. But anyway, y3 is s times x1 minus x3 minus y1. Okay. So that's in the case of the real projective space. That's how you get the coordinates for r. Now you might wonder, that's all fine if you're working over, if you're looking at the solutions to y squared equals x cubed plus ax plus b. But what if you're working in ZP star, where a and b are integers in ZP star, and you're looking for all the pairs of elements in ZP star that satisfy this equation? So it just becomes, instead of an equality, you have a congruence, and all of this is mod p. Well, it's kind of hilarious. Even though there's no geometry at all in this discrete setting, the derivations that we use to get these formulas didn't use geometry, they just used algebra. So, what did I do? I computed this thing. So can you divide in ZP star? So this is division. you can't exactly divide, but you can take inverses. So I could do y2 minus y1 times x2 minus x1 inverse. There's no reason I can't do that. So these are all, now you're imagining that y and x and everything, they're all integers in ZP star. This would be perfectly fine. So I just change all of these divisions into multiplications by the inverse. And all of the algebra that I did in the real numbers would actually go through pretty much the same in ZP star, because ZP star is a field, which means that you can multiply and divide. It's not real division, it's this kind of division, but you can multiply, divide, subtract, and add. And that's all you need to do algebra. So all of these algebraic steps that we took to derive this formula also apply in the discrete setting, and we're going to use the same formulas, even though in the discrete setting there's no geometry and no picture, and it still becomes a group. This is like some deep kind of mystery that you can take equations for these geometric things and then look at these same equations in discrete settings, and similar facts are true. A lot of really modern and ongoing math is centered around that fact. But anyway, so all we have to do to make this into a group rule in ZP star is go through here and add mod p everywhere. And you have to be aware that this is not real division. This is multiplication times the inverse of 2y. This is multiplication times the inverse of that difference. And I add mod p here, and I add mod p here, and I'm done. And what we have now is, we have some elliptic curve, which is just the set of solutions to an equation of this form in ZP star. And now I have a rule for adding them. So if I'm adding p and q, what this is telling me is how to get r, right? So p plus q is equal to r. And I can just do that by transforming the coordinates of p and q. So here are the coordinates of p in the discrete group. Here are the coordinates of q. And I do a transformation on those points to produce the coordinates for r. R is x3, y3. And it's just, now I have an algorithm for making them come out. So here's r equals x3, y3. How do you produce those? You just do this procedure and you get 2 more numbers. And it turns out that is a group. So you get all the good properties of groups, like closure, inverses, associativity, and the existence of an identity element. And I think I already said inverses. Okay, so now we have an elliptic curve group that's defined over ZP star. So we can make one of these for any choice of P, A, and B, provided that it's non-singular. You still have to have that weird relationship between A and B so that the discriminant is not 0. But now you know what an elliptic curve group is, and we can go over to CoCalc and look at one. Yeah, so, oh, that's just the picture. I fooled myself, sorry. I did it again. I'm just going to close that. So right here. Okay, so here's this jumpy, annoying thing. So anyway, here's if you just print out the elliptic curve, I swear, man. Is it going to move again? Okay, so here's the elliptic curve, and if you just make up an equation, so where's the equation that I used to generate that curve? Let's see if we can find it. This is just such torture. It's just, it's moving around at random. Does this help at all? I'm so sorry. I'm not touching my mouse, I'm not touching my keyboard, it's just moving. So here's where I define the elliptic curve right here.
Maybe try holding the little slidey bar on the side. Just like hold that. in place.
Oh yeah, thanks, Aiden. That seems to work. Maybe, no, sorry. Okay, so hopefully you can see this syntax here where I actually define EC. So see, EC is the, so I define G to be Z mod P, and then I pick the constants A and B, which are just -2 and +2. That does work, Aiden, thank you. And now the elliptic curve is just the pairs x, y for x in G and for y in G if the curve is satisfied. And then if I plot them, I get this picture of them. It turns out that there are 31 of them. That's kind of interesting, isn't it? Because, let's see, P was 23, and the number of pairs from the group would be 23 times 23, which is quite a large number. But how many actually end up being on the curve? It's 31. And predicting that number, determining the size of an elliptic curve group after you specify P, A, and B is very non-trivial. So there's not a simple formula that you can use just to look it up. So here I just pick some elements. So P is the 15th one, whatever that is, and Q is the 5th one. So if you look at those, you get these two. So let's figure out what their sum is. So you can use Sage to access the elliptic curve algebraic object, and this is how you specify the curve, and this is how you convert a point into an actual group element. So you'll see now they have a third coordinate. So they're the same as before, but now they have a 1 here, and that 1 is just notation that expresses whether the point is at infinity or not. So it's 1, so these are finite points. If you take their sum, then you get 15, 14. But this sum is computed in the way that is using the group law that we just described. So it's not the case that 10 plus 2 is equal to 15. No, 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 no. It's not that simple. But it's the rule that we just outlined. You can also compute like big multiples. So if you do P times itself 100 times, just by coincidence, you get the same thing as P times Q. You can look at the order of an element. So the order of an element is how many times you have to add it to itself before you get 0. So what this is saying is if I did P plus P plus P plus P plus P 16 times, then I would get the 0 element. And so it's just for general group theory reasons, it's still the case that the order of every element divides the order of the group. And here are all the orders of the elements in the group. So here's a question just to see if anybody's awake. Is this a cyclic group? Remember what that means?
Means that it's not equal to 0, right?
A cyclic group is a group that's generated by a single element. So every element of the group would be like P plus P plus P plus P some number of times. So this group cannot be cyclic because if you look at the order of every element, there's no element of order 32. So an element that did generate the entire group would have to have order 32, but none of them do have order 32. So there's no generator, so it's not cyclic. So I forgot what I was doing here. Oh, here's a cyclic one. So I just made this random loop here to just brute force search for a cyclic group, and I found one with these parameters. So if A is 274 and B is 983 and P is 541, then you get a cyclic group. So let's just see. So it turns out that the order of this group is 521. Notice that 521 is pretty close to 541, and that always happens. Even though I said the number of elements in the group is hard to predict, there is an approximation theorem, which we'll put on the board in a second, called Haases Theorem, which says that the order of the elliptic curve group is equal to P at plus or minus the square root of P. So there's an error term. So the order of this group is 541 plus or minus the square root of 541. What is the square root of 541? I don't know. Square root of, funny. So the square root of 541 is about, let's say, 24. So we don't know exactly what the cardinality of the resulting elliptic curve group will be, but we know that it's 541 plus or minus 24. And it turns out that the actual answer in this case is 521. Okay, so you can pick, what this is doing is picking a generator. So alpha would serve as a generator here. And now beta is equal to some multiple of alpha. So this is just like this is just using the elliptic curve to do public key cryptography. So here now, this number times, so alpha is the generator, beta is the public key, and this number is the private key. And from beta, there's no way of recovering d, which is this constant, that is significantly faster than brute force. So actually there are a couple of methods. We talked about them in class. So there, you might remember that we did generic attacks on the discrete logarithm problem. So those were attacks on the discrete logarithm problem that work no matter what the underlying group is. And those were Shanks's baby step, giant step, which cut the security level in half. And then there was Pollard's row, which was, it did the same thing, but without the big storage requirement of Shanks. So you can still, there are still attacks that cut the security level in half, but the big attack that forced the bit size to have to be so large when you're just doing discrete logarithm problem directly in ZP star is the index calculus. The index calculus, there seems to be no way to generalize it so that it works on an elliptic curve group. It only works on when the underlying group for DLP is ZP star. So for that reason, this is why the security level of elliptic curves is just twice the desired. So the number of bits in the key is just twice the desired security level. It's because Shanks cuts that in half. So that's why you have to double it. But then there's not much else that anybody knows to do except just exhaustively search for the key. Okay, so now, should I have written some of that down? I guess so. I just said a lot, but let me write it down just to make things more clear. Just verbally saying things is not always the best. So what did I just say? Also, let me show off this thing. I think I'm still sharing this, right? So I also made a Python notebook. So this is just straight up Python that doesn't use the Sage library. And so I made like the world's laziest inverse function. And I defined elliptic curve multiplication. So all I did is I defined S exactly the way that we said when I wrote it on the sheet. So this is, instead of division, you multiply by the inverse, mod p. And so this is in the case that this is doubling. Otherwise, it's p and q are different, and s is just the slope. Then you compute x3 and y3 and just return it. So it's super straightforward. And I said multiplication there. That was stupid. I should have called it EC add, because we think of it as addition instead of multiplication. But if you go back to the other slide, what you'll see is that using this function, the sum of p and q is 1514, which is exactly what it was when we used the library. So p plus q is 1514 for these same points. So let me come back to the sheet and just write some of this stuff down. Oh, sorry, I don't think I actually did come back to the sheet, except, okay. All right. Right. So let me just write down Haases theorem. Haases theorem says that, so here, let me just say, knowing the order of the elliptic curve group is hard. So what do you get to know? You get to know P, the prime, you get to know A and B, those are the parameters of the curve. So if you're given P, A, B, and P, A, and B, knowing the cardinality of the curve is hard. But Haase has his theorem, which says that it is it's at least p, basically this is p minus the square root of p. And it's at most basically p plus the square root of p. Okay, so that, you know, Sage can actually compute these cardinalities fairly quickly, and I'll be honest, I have no idea how it's doing it, because let's say that p is roughly 256 bits, so it's 2 to the 256. Then what is the square root of p? The square root of p is roughly 2 to the 128. And so to explore everything in this range, you have to check like roughly 2 to the 128 possibilities. If you're just gonna, which is better than checking, you know, it's much better than checking 2 to the 256 possibilities, but it's still impossible to do by brute force. So Haases theorem is interesting, but basically we're still a long way from being able to compute the cardinality of the elliptic curve. But just know that there are ways. Okay. And so here's one general group theoretic fact, though, that's great. So, you know, just in group theory in general, if G is an element of G, the order of G has to divide the order of the group. So that's Lagrange's theorem. And so that means if we can find P, A, and C so that the cardinality of the elliptic curve is prime, then it will definitely be cyclic. And that's because every element will be a generator. So you just pick some element that has so there are two possible orders here. If this is a prime number, it's not going to be P. It's going to be some other prime. Let's call it Q. So if the order of EC is some prime number Q, what are the possibilities for the order of any group element? It has to divide Q, but Q is prime. What makes it prime? The only things that divide it are 1 and itself. So every element is either a generator or it has order 1, but there's a unique element of order 1, which is the identity. And so basically every non-identity element is a generator. So it's very easy to find one. So we've got something that is very suitable for doing cryptography. That's a cyclic elliptic curve group. If we can just find parameters P, A, and C that make EC prime, which is not that hard to do. I was able to get it to work on CoCalc. I was just kind of tooling around, but it turned out to. So what's going on here? Oh, sorry, that's the Python notebook. But here I just did. Okay, so there we found an example of a cyclic one. But now I'm going to try to go for a prime one. So we don't have to go through all this code. Man, this leaping around is just intolerable. So if what I'm doing here is I'm just picking P, A, and B at random, and I'm waiting to see if the order is prime. And if the order is prime, then I'm breaking. And this is industrial strength here, because I'm picking P to be a random prime that is that's in the neighborhood of 256 bits. So if this completes, which it did, then you get parameters that you actually could use to do cryptography. And so when I did it, I got these. And so I think EC, is this EC still that? Ah, crap. But what about P? What is P? Okay, P, A, and B still seem to be good. Maybe not, but let's see. Sorry if it looks like we're on an earthquake. So we can just make a new elliptic curve. So EC is elliptic curve, and so we have GF. The field that it's over is going to be GFP, and then the parameters are A and B. And right, so EC order is that, and is it prime? Okay, it's prime, and so we can use sort of any element of it. Can we do like alpha equals EC, I don't know, 18 or something? And what is alpha? Oh, sorry, it's too long to do that. Random element. So that's alpha, and you can figure out the order of alpha. So is it true that alpha.order is equal to EC.order? And the answer is true, so that means that alpha is a generator for this group. So now we're ready to do some elliptic curve cryptography. So you pick D, which is some secret. So D would be like a, man, I think it's not somebody jittering the screen somehow, because that would be too cruel for a human being to actually do, right? Nobody would still be doing it now. Okay, it's moving, not moving. So this will be some big random number. Randant, so something between 0 and like 2 to the 256. So let's see what we actually get. So D turns out to be that. And now we could do beta is equal to D times alpha. And what is beta? Okay, all right, it's that. And I'm just about to vomit. I don't know about you guys. Jesus. So anyway, so there's beta. And there's no way, once you're given beta, there's no way to recover D, except for Pollard's row or Baby Shanks' giant, Shanks's baby step giant step or something like that. So you could actually use this public-private key pair for any cryptographic application that uses discrete logarithm problems, such as the digital signature algorithm. So this gives rise to EC DSA, which is a very popular signature algorithm, elliptic curve digital signature algorithm. And you can also do elliptic curve versions of Al-Gamal and also elliptic curve Diffie-Hellman key exchange. So, so what else? Oh, there's this kind of interesting controversy about the elliptic curves that were offered by the so the NSA just defined some standard curves, and you can see here, I had the document open for a while. So are the Nist standard elliptic curves backdoored? And I had the actual document open. Let me see if I can find it here. So that's what I'm looking at, and pretty sure I have the thing open in some web browser. Okay, it's not there. Is it over here? Oh, so this is annoying. And stupid zoom option. And look at it, it's still thrashing down there. So I'm sorry, I seem to have lost it. But if we go back to the Wikipedia, sorry, the slashdot thing. So are the Nist standard elliptic curves backdoored? So they defined a bunch of these standard elliptic curves. So they did something similar to what we just did. They found parameters P, A, and B so that the cardinality of EC is a prime. And so how do they choose these parameters P, A, and B? So they could just do it randomly, and that's basically what they did. But then the NSA says, well, here are these numbers that we found kind of randomly. And so you just have to trust that they actually did find it through some random process. By the way, I have complete trust in the NSA. I'm glad the NSA is out there. Even with what's going on and like our ridiculous administration, I still trust the U.S. government. But some people obviously, like if you're, let's just say that you work for some adversary of the United States and you don't want to use any cryptography that has been backdoored. Maybe even if you are not worried about the NSA abusing your information, you just don't want to use backdoored constants because you're afraid that might reduce the security and somebody besides the NSA might figure that out. They give you these parameters P, A, and B, which are generated by a random process. So in order to give the public confidence that those parameters really were random, what they did was they picked a number and then they applied a SHA-1 hash to it, and then the outcome of the SHA-1 hash was used to generate the parameters. So there's so that affords some level of protection there. So because SHA-1 is a hash, which is supposed to have pre-image resistance, they couldn't just make any number come out of the SHA-1 hash that they wanted to. So they pick an input, and then theoretically the output of SHA-1 is like a pseudo-random function of that input. And so that should really be a random determination of the parameters P, A, and B. So the way to do that that would instill the most confidence in the users is if they just hashed sequential numbers using SHA-1 until they found one that produced suitable parameters. So in that case, the input to SHA-1 should have been some number that's in like the billions or trillions or maybe quadrillions. So by the standards of the very large numbers that you work with in cryptography, it should have had an enormous number of leading zeros. But what this article is saying is that it wasn't a number like that. It was a 256-bit number. So why was it 256 bits? Doesn't really need to be that big because they can't try 2 to the 56 possibilities. They can only try like 2 to the 64 possibilities. So why don't they use a 64-bit number instead of a 256-bit number? So this made people suspicious. And so this guy, Bruce Schneier, who's like the secular saint of cryptography, he's very smart, he's usually right about things, thinks that 256-bit number was picked very particularly using some kind of the enormous brute force resources of state-backed cryptographic agency to generate parameters that have the properties that they wanted, and then there might be something about the algebraic structure of the elliptic curve that generates that the NSA knows that allows them to determine D from the public parameters in a way that's better than brute force. Yeah, Aiden?
Yeah, that's kind of something I was thinking about, like how we use like P and Q to kind of find the elliptic curve, and to me that kind of seems weird if you're trying to find like random primes, like if there's a sort of like pattern to it, like I don't see how that would be like secure. I kind of understand what you just said about like maybe they kind of like that sort of thing because it's more predictable.
Oh, you mean the SHA-1 step? Why not just pick a random prime and random A and B?
But like with the elliptic curves, like you could use algebra to kind of like figure it out. I feel like RSA kind of has more layers to it, like, and more complexity.
Mm-hmm. Yeah, well, it's definitely true that in the public domain world, there's no attack on an elliptic curve group that will reveal the private key that works on every elliptic curve group. But it might be that that for these parameters, there's some special weakness in the particular elliptic curve group that they chose. So some attack is possible just on this particular algebraic object that doesn't work for all of them. So there's some tricky fact about the elliptic curve that corresponds to this, for example. So this is a particular curve, sec p 256r1. So there might just be something about that lets somebody break a signature, for example, not in 2 to the 56, not in 2 to the 128 steps, but in like 2 to the 85 steps or something like that. And so that might be true. As for whether like RSA or elliptic curves is more complicated, I don't know, because there might be, you know, you can imagine tricks with RSA too. Um, but the thing is, like, nobody, there's no government agency that's picking, like, well, maybe there is, I don't know. But when RSA is used, I don't think it's with, obviously it's not with standard primes, because it doesn't work if everybody knows what the primes are. So every time you establish an RSA session, you know, P and Q are the secret. So the parameters are the secret. But in the case of elliptic curves, D is the secret and the parameters are public. So the government agency can determine the parameters, and then, you know, the secret is just whatever you choose. But with RSA, the parameters are the secret, and so everybody has to choose their own parameters. And so there's no NSA primes, because it just doesn't make any sense, because knowing the primes breaks the cipher, so they can't publish them. So that's kind of interesting. Like I said, like I'm, you know, for on average for the last 50 years or so, I think the government has done a relatively good job with people's privacy, with a couple of outstanding counterexamples, like you know, Martin Luther King and J. Edgar Hoover and things like that. But for the most part, like as far as I know, people are not getting massively blackmailed because the NSA is decrypting their private communications. Whereas I just think probably on balance, it's better for them to be doing whatever they're doing. But you know, opinions vary, and maybe you think something else. All right. So, but that doesn't mean that the conspiracy theories are not true. The conspiracy theories are definitely true. It's just that, you know, for the most part, the objective of the United States government is not to kill its citizens, which a lot of people seem to believe now for some reason. Like my wife is really nervous about drinking fluoridated water. And obviously the government believes that on balance, it's better for citizens to drink fluoridated water. So the expected benefit to drinking the fluoride it's got to be positive, otherwise they wouldn't do it. It's not like they want to hurt people, you know. But everybody's in such like a weird frame of mind now with I don't know. So that's the moment that we're living in. But I should have stopped recording this a long time ago.